Yep, example 3 and 4,
Finding
and that's what we're doing for today. So,
finding the error bound.
yes,
That's what we're doing.
that's what we've been doing, and that's what we're going to continue doing for this section, finding the error bound.
I just realized.
So, example 3, that's where we're at. This one's considered a no calculator question. So on an AP exam, it would actually be no calculator. If we want to use it to reduce some numbers, we can if we want to, since we're in class here. But on an AP exam, this would be no calculator. So it says, write the fourth degree Maclaurin polynomial for f of x equals e to the x. Then use your polynomial to approximate the square root of e. And find a Lagrange error bound for the maximum error when the absolute value of x is less than or equal to 0.5. All right, so the first thing we need to do, they're talking about the Maclaurin polynomial of e to the x. And they said fourth degree. So what would that be? Maclaurin polynomial, so think Taylor series, but remember Maclaurin just means the center is at 0. So Taylor series for e to the x, and they want a fourth degree.
1 plus x plus x squared over 2 plus x cubed over 3 factorial plus x squared over 4 factorial.
Yeah. Now, this is a Maclaurin polynomial, equal sign or a squiggly sign?
Really?
Squiggly. It's approximate. If it's the series, the infinite amount of terms, then it's equal. But this is the polynomial. Okay. What was that, Harry? All right, so now we want to approximate square root of e. So really, how can we use this to approximate square root of e? Yeah, 1/2, because the square root of e is actually e to the 1/2. So e to the 1/2 is approximately, using a fourth degree, 1 plus 1/2. And since it is non-calculator, you could just leave it as 1/2 squared over 2, but I think some of these numbers we can simplify out. So that would be 1 over 8. And I worked out some of these ahead of time, so I'll help you out with the math. The next one, 1/2 cubed over 3 factorial, simplifies to 1 over 48. Again, if you're on an exam and you're timed and rushed for time, just leave it as 1/2 cubed over 3 factorial, and that's exactly what you need. So this is just a reduced form of it. So if you're pressed for time, just leave it in that form. And the last one, again, after doing some calculations, would be 1 over 384. And if you had the time to get a common denominator and add them up, you would get 633 over 384. So again, another thing you could do that I want to explain for this problem, again, if you're pressed for time, that way you know you could get on to part B. So if you look ahead in this problem, they're not specifically asking, like some problems, what's an approximation specifically of like this 2.3 and is that in the interval? Like asking if something's in the interval. Since they're not asking this, if you're pressed for time, you could just say, okay, this added up equals A, some value A. And then when you get down to this part, which we're going to calculate the error bound down there, we're going to actually do it. But again, if you're pressed for time, you can say, my interval is this A value, whatever it was that this right here, minus the error, and then A plus the error. So again, if you don't have time to find that common denominator and actually figure that out, you could just call this some value and use that same value in part B.
And they won't dock points on the AP test?
According to what I've seen, I don't think so. Because you're saying this is equal to that A value, and they're not asking specifically in this question, is 1.765 in the interval? If they're asking that, then yeah, and most likely it's a calculator question, you need to know exactly what those are. But you're saying, I know these added up equals some value A, and I'm showing you, I take this value A, I subtract the error. I take this value A, add the error. The concept is right there. You're showing them exactly what you're doing. You just didn't have the simplified version. If you have the time, I would go this route.
So could we have done that even earlier, like before we plug in 1/2 and then you just set it equal to a, like before simplifying any of the fractions.
Like up here, leaving it in this form?
Yes.
Yeah, that's what I'm saying. Because it's a non-calculator, yes. That's what I would, if especially pressed for time. You don't have time to do all that work, simplify this, and get this. You could say with 1/2 plugged into all of this, it's equal to some a value. Okay. All right, so 633 over 384 is the approximation of e to the 1/2. So now what we need to do, it says find the Lagrange error bound when this x is less than or equal to 0.5. So they're telling you they want it to be less than 0.5, or at the most 0.5. So if we think about the derivatives here, because we're at a 4th degree, so which derivative are we actually looking at? The 5th, the next one, the n plus 1 derivative. With e to the x, if you take the derivative to the 5th derivative, what are you going to get? The 5th derivative of e to x is what? E to the x. Okay, that's not bad. So graphically, just drawing a little picture to understand what's going on, e to the x looks something like this. Okay? With this being 0. And they're saying the absolute value of x is less than or equal to 0.5. So all the further they want you to go is 0.5 or 1/2. Okay? So we're looking at this interval. That's what they're telling you. So visually, this is what we're trying to see. So again, we want to maximize or find the maximum value of the derivative on that interval. Well, where does that maximum value happen? At that point right there. That's the highest point on that interval. So at e to the 1/2, that is the highest point. So as we set up our remainder, again, this is same formula we've used, the Lagrange error bound. Yeah, go ahead.
You said that the interval we're looking at was from 0 to 0.5, correct?
Yes, because they're telling you right here in this one.
So couldn't it have been negative 0.5 to 0.5 though? Because the absolute value of any of those negative numbers will also be less than 0.5.
Can you say your question again, Eric?
So, I mean, I know it doesn't change the outcome, but
Yeah.
It says the absolute value of x must be less than or equal to 0.5.
Mhm.
So why isn't our interval from negative 0.5 to positive 0.5? Because all the values in there are less than or equal to 0.5. Why is it only 0 to 0.5? I mean, I guess it doesn't change the outcome. I'm just wondering.
Yeah, it's probably dependent on the function. If it was a function where it would matter, they probably wouldn't have had the absolute values. But in the terms of the e to the x, like you said, we know they're all less than 0.5. So that's probably why in this particular question, they're saying the absolute value of it's less. It really doesn't matter. We know they're less than that. But it's probably, when we use a different function, there's probably a scenario where we have to use the absolute value, so they're keeping the procedure the same. But yeah, I'm not sure exactly, because we know for sure that it is less than 0.5 anywhere, or yeah, all x's are less than 0.5.
Mm-hmm.
Yeah, I'm not entirely sure. Okay.
That's all right. I don't know.
What was that?
That's all right. I didn't know.
All right, so R4 of the 1/2. Again, the Lagrange error bound theorem, absolute value. And again, this is the maximized value of the derivative. So I will write it out again. That's f of 5 of some z value over, we're talking about f of 5, the n plus 1 derivative, so over 5 factorial. What x value are we looking at again? Where was the x? What x value was the derivative maximized at? Was that 1/2? So that's the x value we're actually using. They told you 1/2. Minus, well, 0, it's Maclaurin. I'm not going to write the minus 0. But minus 0 here because it's Maclaurin. You minus your center. And that's to what power? Remember, it's very similar to a Taylor series. We have 5 factorial, so this is to the 5th power. 5th derivative, 5 factorial, 5 power. So again, we don't know the z value, but we do know the maximum error that we can have, or the maximum potential of that derivative on that interval from 0 to 0.5 would be e to the 1/2. E to the 1/2 is going to give us the maximum value of that derivative on that interval. So we know e to the 1/2 over 5 factorial and 1/2 to the 5th.
Third or 1/2 to the 5th?
That is,
Of our interval?
yeah. That's the x value that we're at minus our center. And we said we're at that 0.5 because that's where it was maximized at.
Okay, so 0.5. So that's where you evaluate it from.
Yeah.
So that's where our was.
Yeah, if you remember back to yesterday's problem, we had 1 minus 0 because 1 was that value where we found where that one was optimized or maximized. Yep. Okay. So at this point, again, we know we found the approximation of e to the 1/2. Remember, we found that approximation over here. So that approximation, I know this isn't for part B, but I'm going to run over into part B here, is 633 over 384 over 5 factorial, and then 1/2 to the 5th. Again, worked out ahead of time, 1/2 times 1/2, 5 times, gives you 1 over 32. So again, like I mentioned earlier about this part over here, calling this some value a, that would be the value a right here. And then again, if you don't completely simplify this, you could just use this part here, and then your part B, your interval could be a minus, and just write this whole term. And then it could be a plus, and write this term. But since I have it worked out, we're going to write out a little bit more simplified version. So it'd be 633 over 32 times 5 factorial times 384. Again, so it's non-calculator, so we don't have a decimal of it, but this is our maximum error within that interval. So that's what they're asking for in part A. Use e to the x, Maclaurin polynomial, 4th degree. We did that. Estimate at 1/2. We were able to do that. Use Lagrange error bound, or Taylor's theorem, for finding the maximum error. Well, we found the maximum error right here. And again, we drew the picture to help us visualize where that would be maximized, and it's maximized at 0.5. So now part B is just wrapping it up. Question, Caitlin? Jeez.
Well, just how did, since like the 633
Yep.
over 384 over 5 to the factorial, how did they end up on this? How did both the 5 factorial and the 384 end up on this bottom?
Because when you have, let's say, A over B over some C, fraction over fraction, this is going to multiply by the reciprocal, the C. So you're actually going to multiply by 1 over C. So you would get A over B times C. Does that help?
Yeah.
Okay, so now part B is just creating that interval. So again, the interval would be 633 over 384. And again, that's where I mentioned from up above, if you didn't have that completely calculated out, this would be your value A. And we're actually going to write out, since we didn't have a calculator, we're going to write this whole term. It's 633 over 384 minus the absolute value of 633 over 32, 5 factorial, 384. That's the lower bound. Then the upper bound. So again, we don't have nice decimal or fractional answers to look at. It's kind of a mess here. But we're guaranteed by Lagrange's theorem, with this remainder theorem, that our actual value of e to the 1/2 is within this interval. So that was our approximation, but we know for sure that it's within that interval. I think example 4 we'll like a little better because we can use a calculator and actually get some decimal answers. All right, was everybody able to get down example 3? Caitlin, you need me to read something? Still copying? I know it got kind of smashed at the end here. Good? So we need to think way back with this example to the beginning of the Taylor series. So the first way we actually computed or found Taylor series. Now they did some of the work for us here, but calculator permitted. The function f has derivatives of all orders for all real numbers x. Assume that f of 2 equals 6, f prime of 2 equals 4, f double prime of 2 equals -7, and f triple prime of 2 equals 8. So again, thinking back to the original section where we started Taylor series, we found all those derivatives. We evaluated the derivative. In this case, it's evaluated at 2. And then we actually created our Taylor polynomial, our coefficients, our factorials, and exponents. So we want to write a third degree Taylor polynomial about x equals 2 and use it to approximate f of 2.3. Give 3 decimal places. So we're going to create some polynomial, f of x. Again, it's a polynomial, so squigglies. So think about how we created the Taylor polynomial. Think about the terms. It's what plus what plus what plus what. Where are the factorials, the powers, and coefficients? So what term comes first?
6.
Yes, 6. That's the first one. 6 plus
4. No, 4x minus 2.
Exactly. Don't forget the center now, they're saying it's about x equals 2. So 4 times x minus 2. Again, remember the derivatives evaluated are all of your coefficients. So the next one, we now have, it's -7, so it's actually -7 times what? We know we're going to have an x minus 2. But what else do we need?
1 half.
Okay, so it's all over 2. I need one more thing. Look at each.
Your x
It's, yeah, squared. Okay, very good. We have one more to go. The third derivative, it said, is 8, so plus 8. X minus 2 to what power? Cubed. Over what? 3 factorial. Again, no dot, dot, dot or anything. This is just a polynomial, and it's a third degree because we went to the third power. There are 4 terms, but it's a third power. So be careful whenever you go to some of the questions. If they say, give me 4 terms of the series, well, that's listing out 4 terms in a series. This is a polynomial. When they say degree, you actually look at what the degree is. This is a third degree, even though there's 4 terms. All right, so next, now we need to approximate the value of f of 2.3. So f of 2.3. So you're going to need your calculator. You're going to plug in 2.3 to all of these x's and find an approximate value. So it's going to take a little bit to type that in, but go ahead and approximate f of 2.3. All right, did we find a value? 3 decimal places. You have it, Caitlin?
6.921.
Yeah, 6.921. So this is our approximation using the third degree polynomial. Is that what everybody else got to?
Should it be squiggly?
I guess technically, yes.
Um,
Well, this here is equal to that,
Is it?
which is the approximation of that. But if you want to, I'll put them. There you go.
Oh, I just wanted squiggly.
All right, so back to Lagrange error bound. Fourth derivative of f satisfies the inequality. So what we're saying, the fourth derivative is bounded by this value of 9, so it's no greater than 9. It's less than or equal to 9. For all x values within this interval, 2 to 2.3 we're talking about. So 2 was our center, 2.3 is the value we were approximating, and we know in that interval there is no value for the fourth derivative greater than 9. Use Lagrange error bound on the approximation of f of 2.3 found in part A to find an interval of AB such that f of 2.3 is between A and B. Give 3 decimal places. All right, so the remainder, or the error. We have R of 3, so we have to use the fourth derivative, and that's what they gave us. So f of 4 of some x or z value, some unknown z. 4 factorial. What are we multiplying by over here? Again, think that's x minus c. What's my x? What's my center? So what am I multiplying by here? Autumn, do you have this part in the parentheses?
2.3 minus 2.
Yeah. 2.3 minus 2 to the fourth. Again, before we use the calculator, because we are allowed to use it, we can simplify that a little bit. They're telling you the maximum that this derivative can be is 9. So 9 over 4 factorial. Again, that given information, 9 over 4 factorial, it's going to be 0.3 to the fourth there. Now we can use our calculator to find our maximum error within that interval. Did anybody find it yet? I know it says 3 decimal places. I have 5 in my answer because the first 2 were zeros. Yeah. I have 0.003. I have 0.00304, but in grand scheme of things, that far out is not going to be a major difference. So my remainder maximum error, the net interval is 0.00304, so very small. So again, now, based on our error, we need to find the interval for part B. So the approximation from part 1, 6.921, minus this error. And I'm not going to show the work here. Go ahead and calculate it, and we'll just write down the values. So 6.921 minus your error gives you what value? Shouldn't change too much. Yep. 6.918 rounded. Okay. That's the lower bound. And the upper bound I got was 6.924. Okay, so very small interval. So 6.921, right in the middle of that was our approximation. Very small interval though, we know for sure that f of 2.3 has to be within that interval. So part C, based on the information that we have above, could f of 2.3 equal 6.992? So based on all the work we did above, could that be the answer? Nope. No, since 6.992 is not in the interval from part B. Again, and that ends example 3 and 4. 5 is a little longer, so we're going to take our time on that tomorrow. We're not going to get into that.
I have a question.
Yeah.
In the past, we were, with paradigms, we had to, like, supplement to figure out whether it was open or closed. Why don't we have to do that here?
So with these,
Yeah.
well, you could, but in this case, this one is less than or equal to, so it could be equal to those. So you could base it off of that. Let's look at the previous one. Again, example 3 was less than or equal to, so that was included.
Oh, I see. At the bottom it has the, your F value is less than or equal to B, greater than or equal to A.
Mm-hmm.